Point one, we introduce a dummy variable into the regression. We need to make extra assumptions in addition to 1.5. So this question is implicitly telling you that 1 to 5 hold in order to obtain unbiased estimates of the partial effect on the new dummy variables. However, we do not require extra assumption to obtain unbiased estimate of the partial effect of the other continuous variables discussed. The very simple answer is, if you look back to the assumptions of the OLS, there is no mention that the variables need to be continuous or discrete or dummy variables. Okay? So if you have assumption 1 to 5, then you can rest assured that it will also be unbiased, right? So you'll still get those same results. So that's, in short, question 1, okay? So we didn't need extra assumptions. Now, we want to understand being good looking, helping individuals earn a living. So if you look at this regression here, okay, how do we interpret beta hat looks? Okay, well, looks is a continuous variable, if you like, or it takes value from 1 to 5. So the way I interpret this is an extra unit of looks, right? So if you are a little bit better looking, your earnings will increase by $0.19 or 19 cents per hour. Is that statistically significant? How do you check statistical significance? You do a t-test. What is the t-test? 0.19 divided by 0.19 gives you 1. Because it is within minus 1.96 and plus 1.96, you fail to reject that beta is equal to 0. So you say it's not statistically significant. Right? How do you interpret the coefficient of beta hat females? Well, first of all, we notice that it's negative, meaning being female lowers the average earnings by $3.1 per hour across all levels of educations. Okay? Female is not being interacted with education, which means that difference of minus 3.1 is the average difference between male and female of different looks and of different education. Right? Note another thing. The modeling that we've done here is assuming that looks is affecting males and females exactly the same way. I'm not interacting looks with males and females, and it might be different, right? So we might actually notice a difference in that effect. Okay. How do you interpret beta hat education? Well, beta hat education is simply telling me that an extra unit of education increases the salary, the hourly wage, by 37 cents. Is that statistically significant? Yes, it is. Is the effect of female statistically significant? Yes, it is. How do I do that? I do a t-test. Okay. What's the t-test associated with the female coefficient? Is minus 12, or something higher than minus 12, right? What's the coefficient associated with education? Is like 9. Okay. So those are big statistically significant coefficients. Okay. Next, we move on to this idea of looks. If you think about it, you're trying to get some sort of pattern or structure of this looks variable by not looking at it as a single variable, by dissecting it into different dummy variables. So you have looks 2, looks 3, looks 4, looks 5. Now, how do you interpret beta hat looks 2, this minus 0.10? Well, the way you interpret it is you have to take care of what is the base category. What's the base category here? Is looks 1. What do we expect? So then what's the interpretation? Is that people with looks 2 earn 10 cents less than people with looks 1. Is that statistically significant? The answer is no, because I do 0.10 divided by 1.2 will definitely be something less than 1. Okay? Or greater than minus 1. Okay, how do I interpret, for example, looks 5? Well, the people that have looks 5 earn $1.60 more than the people with looks 1. Is it statistically significant? The answer is no again, by applying a t-test. Right. Is there any statistical significance across the different groups? The answer is no. Does the size relative to the coefficient beta 2 looks, beta 3 looks, and beta 5 looks make sense? Well, it makes sense in what perspective? In the perspective that what did the researchers expect? The researchers expected that the further up the looks you go, the higher the wage would be. Okay, is it as expected? Well, first of all, beta looks 2 is negative. We should have expected all of them to be positive. What else should we have expected? We should have expected that all of these coefficients to be increasing as I go to different looks. So it is true that from looks 2 to looks 3 I have an increase, but I have a decrease for being in looks 4. Okay, so that pattern is not right as we expected, right? So making sense, we really need to elaborate on what do we mean by making sense. Okay. Okay, then we go to this final bit where we look at below. How do we interpret below? Where below is when you are of looks 1 and 2. So if your looks are 1 and 2, you earn 79 cents less than the average individual with looks 3, 4, and 5. Is that statistically significant? The answer is now yes. Okay. Now, what's the danger with this? With this as a study, is that it seems like the authors wanted to find a relationship with looks, okay? Or whomever wrote the question wanted to find the so they start off with some, they couldn't find it, changed the definition to something else, couldn't find it, changed the definition to something else, finally found it, and come up with a conclusion, right? No one really likes to read that something is not statistically significant, right? So if this was a real a paper, you would be a bit skeptical of this just because of the different approaches that they took until they found something that worked. And you'd be even more skeptical if they didn't report the other two things that they had done, right? So they just reported this final one. And they pretended that this was the hypothesis all along, right? And that's what they wanted to test. And unfortunately, this happens, that people try a lot of things and just tell you the ones that sell a good story, right? Just like the journalist picking and choosing from the stories, right? The academics also, sometimes, not all of them, would pick and choose the results and then decide what to report. What's the good news? You're taking MG205, which means you can make up your mind on your own, right? You can look at stuff on your own and decide whether something is robust or not, and not let the media or some expert or some big shot professor somewhere tell you what's right and what's wrong and what's robust and what's not robust. Okay, right. So that's that question there. 5.3. In our large organization, we have men, women. We'd like to understand how the salaries that our employees earn depend on their years of education, years of experience, and position. We are not sure whether we should run two separate regressions, one for men and another for women, or whether we should run just one regression. How can we choose what is the right model to estimate? I've made a video on choosing between different regressions, but the big picture here is you will have a general model that would allow for differences across male and female across all the variables that you have. Okay, so this model here, if you like, is the unrestricted model. This model, what are the variables that you're looking for? Education, experience, manager. This would have been the regression if you were going to run a single regression for all of them. Because you're not sure whether you should run a separate one for males or females, means that you're assuming that all of these coefficients could possibly change between male and female. If all of those coefficients could possibly change, bless you, then we need to interact all of them. We need one for the intercept, we need one for the interaction between female and education, female and experience, female and manager. You need all of those interactions in order for that to work, okay? And in MG205, whenever someone says, how do you choose between two models, you should always think F-test, okay? Because this model, the big model, the green model, will collapse into the blue model if and only if beta 4 is equal to 0, beta 5 is equal to 0, beta 6 is equal to 0, beta 7 is equal to 0. Here you have it. That's your null hypothesis. That's an F-test. Okay. And of course we could do this F-test if we had all the ingredients. We don't have all these ingredients, so we could stop here. Okay. we could stop here, right? Even though, I mean, we could write down what the f-test is, but we don't really know the ingredients of the f-test. We don't have the residual sum of square of the restricted or the unrestricted model. Okay? So in an exam, you could have just stopped there. Okay, 5.4. Assume that in our country there are 3 universities, LSE, Oxford, and Cambridge. We want to understand whether graduates from these 3 universities earn different wages. What empirical model would you propose to study this? We also want to understand whether wages increase with experience at different rates for graduates from these 3 universities. What empirical model would you propose to study this? Okay, so it seems like we have 2 parts to this question, right? Just one looking at the changes in salaries, and one looking at the changes in salaries including experience as well. Okay, so the first model is very simple. You just have to include dummy variables. How many mutually exclusive groups do you have? 3. How many dummy variables will you include? 2. Good. And then the moment you have experience, the simple regression, if I were to stick with the same thing, the blue regression, right, would be alpha, and you'd have some experience, right? That would be the simple regression. But if you want to include, more stuff to that, then you're going to have to interact. You're going to have to allow the alpha to change for different universities. So we're going to have this intercept dummies. Let me go with green because we're going away from that simple model. And we're going to allow the LSE and Oxford to interact with both experience. Right? So we have experience in Oxford, experience in LSE, so we can get those 3 separate regressions effectively, okay, for the different bits. So in this model, we allow intercepts and slope with respect to experience being different from 3 universities. Running a single regression would have given us this. We therefore need to test, right? If we were to run a single regression, which is the blue one, we want all the green bits to equal to 0. Okay, we want all the green bits to equal to 0. And that's why we have this f-test. This is how you construct this f-test. You should know by heart this formula, right, for the general case. And that's how you do that, question 5.5.
Would it be possible to see those things on the screen, or is there something that doesn't work?
No, you're just being very shy. Thank you. What an improvement. Wow, brave man. Okay, when that happens another time, don't let me talk for another 20 minutes or so before you realize that. Okay, right, 5.5. We believe that earnings of men depend on their education according to the following function. Everything was being recorded, by the way, so you can go back to this. You'll be able to see everything. You just, it's a shame that someone else didn't point that out a bit earlier. We believe that earnings of men depend on their education according to the following function. So we have male and we have female. Note one thing, the intercept could be different. The slope could also be different. If we want to do this in one equation, right, use a dummy variable to capture gender, write down in a single equation how the earnings for workers depend on his or her education. If we're going to do this in a single thing, we're going to have to allow for both the intercept to differ. So this is allowing for the intercept to differ. This is allowing for the slope to differ. Okay. What was D here? D1 is male. Okay. So when D is equal to 1, your L wage becomes delta plus phi plus mu plus lambda times education. Agree? This is the male regression. If this is the male regression, well, this is the intercept for the male regression. This is the slope for the male regression. What is the intercept for the male regression? This. What is the slope for the male regression? This. So then, this thing here well, actually, if you look at this bit here, this is the slope of the male, right? This is the intercept of the male, okay? And that's how you do that, right? Sorry, I thought this was on silent. That's that part over there, okay? So this question's boiled down to you just really writing a big picture of this stuff, right? Writing a big picture of this stuff. In our course, there are students of 10 different nationalities. We want to understand whether students of different nationalities get on average different grades. What empirical models would you propose to study this question? How many nationalities? 10. How many dummy variables? 9. Right? So the moment you got there, k goes from 1 to 9. Right? So someone asked about this sigma notation with the dummy variables. Is really just alpha plus beta 1 times nationality 1 plus beta 2 times nationality 2 plus beta 3 times nationality 3 ... But there's a better way to write it, and it's just to use the sigma notation, because I don't have to write 9 of them, right? But I can just write that sigma notation. Right, what's the interpretation of the coefficient? Well, what is the base group that we're looking at? The base group is nationality 10. So all the coefficients will be with relationship to nationality 10. So if it's positive, that means that if beta 1 hat is positive, that means that nationality 1 has a higher sample average grade than nationality 10 by exactly that amount. Okay, 7. We've obtained the following OLS regression results, where male is equal to 1 when the individual is male, female is equal to 1 when the individual is female, age is age in years. Robust and errors are in parentheses. Draw a function in the age-wage space that represent how we are predicting earnings to change with age for men. So we're looking at men, right? Men means female is equal to 0. Men, so this goes away. Men means that this equals to 1. This also goes away. So what do we have? We have minus 2 plus 10 times age minus 0.1 age square. That's what you have, okay? So when age is equal to 0, you go to minus 2, okay? What's the slope at age is equal to 0? The slope just at age is equal to 0 is 10, right? Because what's the derivative of this with respect to age? Is 10 minus 0.2 times age, right? So what happens to this slope as age increases? This slope gets shallower, right? Shallower and shallower over time, okay? Everybody with me? And that's how we get to this. It's a concave function. We can do a similar thing for females. So if we go back to females, if male is equal to 0, this will go to 0. This will be equal to 1. But what you notice is that you have 0.1 here, and you have minus 0.1 here. This h squared term will disappear, right? And then you have minus 2 plus 3. The intercept will simply become 1. 1. And the age, the slope in front of the age, is just 2. So you're going to come up with a linear function, okay? This is a nice little exam question, for example, just to get the students understand how dummy variables enter the different regression, how the fitted lines get about, and a bit of algebraic manipulations. Yes, everybody with me? Yeah? Okay. Excellent. So far, so good. 5.8. We believe the effects of competition might be different for longer routes than for shorter routes. For instance, customer loyalty, blah, 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 blah. We'll go to here. What is the marginal effect of competition on L fares? How are we going to do that? I'm just simply going to do a partial derivative. Minus 0.43 plus 0.05 L distance. That's the marginal effect of competition on L fares. Is the marginal effect increasing or decreasing? Well, it is increasing in L distance. The larger is L distance, the larger is the marginal effect. You do a similar thing for distance on fare. Is the marginal effect increasing or decreasing? Again, will be increasing. Test the hypothesis beta competition is equal to 0. So if I'm focusing on this, beta competition is equal to 0. How I'm going to test it? I'm going to do a t-test. Minus 0.43 divided by 0.30 is approximately 1.33, right? Maybe 1.35. Regardless, we will fail to reject that beta comp is equal to 0. Okay. Here's the tricky question. Does this imply that comp has no effect on L fares? Some students might be tempted to say, oh, beta comp is equal to 0, therefore, this implies that comp has no effect on L fares. Why would that be wrong? It would be wrong because competition enters here, but competition also enters here. So competition is affecting L fares through this and through this. So the only way that you can say that competition has no effect on fares is if both of those two coefficients were jointly equal to 0. If they're not jointly equal to 0, then you're into trouble. Okay. Right. So we need to differentiate with those solutions. We don't care about them. 5.9. We want to understand the effects of education and employer size on individual salaries. So we got to here. How do you interpret beta hat education of 0.07? This is a purely interpretation type thing, right? So in this particular situation, education is in units. Here you have log wage, so an extra unit of education or an extra year of education increases wage by 7%. What about L sales? You have log, so the interpretation is that of a elasticity. So a 1% increase in sales increases wages by 0.24%. Okay. If we wanted to include a variable capturing the employer profits in a regression, would it make sense to convert it to logs when adding it as an explanatory variable? Okay. Well, we have profits, right? But we know that profits can be either positive or can be negative. So logging them might be problematic, right? Right? So that's not something that, that we would want in this particular case. Even though in first principle, logging profits, if we didn't have this negative number problem, it would have been a bit more interesting because we would expect the percentage change in profit to affect percentage change in wages, right? We wouldn't have expected actual absolute value of profits. It would be more meaningful to look at percentage change in profits than percentage change than actual change in profits. So in that sense, logging it has some appeal into how it will change the interpretation. Unfortunately, because of these negative values, it's going to be problematic. Okay, so logging it will be problematic. Okay, 5.10. I believe that relationship between an individual's salary and his years of experience is concave. In other words, salary increases initially with experience, but decreases at a decreasing rate. It reached the maximum of around 55 years and blah, 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 blah. What population model would you think would capture the relation between salary and experience? Because you want something that's concave, you need to have quadratic bits into that, okay? So you have experience and you have experience square. So those quadratic bits are going to be important. Okay. If my hypothesis is correct, what signs will the coefficient of the OLS regression take? Well, if you take a concave function, what do you know about the concave function? What do you know about the second order derivative of this concave function? It's negative, right? Think of a negative concave face, right? So if it's negative, then I want my beta 2 to be negative and my beta 1 to be positive. Okay, 5.11. In our company, we randomly gave between 5 and 25 hours of training to our workers. Then we ran the following regression. What is the partial effect of an increase in training for 1 hour? This is standard. What is the effect subject to economies of scale? Standard. What is the value of hours at which the partial effect is the highest? What is the value of hours at which the partial effect is the highest? Well, that should be relatively straightforward. If the partial effect is this, right? That partial effect is increasing with hours. So what do you want hours to be? The highest you possibly can get them, right? In this case, 25 is the highest. Okay, 5.12. We run the following regression of earnings on experience and experience square. Can we conclude that workers' earnings change as they accumulate more experience? Here's what would have been problematic here. If you look at this coefficient, is it statistically significant? The answer is no, t-value of 1.5. Is this statistically significant? No, t-value of 1.5. But experience enters here and here, right? So if it enters on this 2, right? If it enters on this 2, then we need an f-test to do that. If you want to say that experience doesn't have an effect, then you should be able to claim that it won't have an effect through this term and it won't have an effect through this term. You need an f-test. Okay?
And so
yeah.
The effect of one f-test can be different from
of
the
course.
effect of those two tests?
Of course. Of course. So it's a bit of a trap here, right? Because students might be inclined to say, oh, the one is statistically insignificant, the other is statistically significant, so yes, experience doesn't matter. But really what you need is a joint test there. Right. Similar situation, we look at concave. Does our line suggest the concave relationship? Yes, it does. At what point is the marginal effect the highest? So similar thing as before. I think that question is something that you could easily do. 5.14. Now, this is interesting. We have this regression, and we're being asked to plot this regression. Well, what are we explaining? So what should be the y? Productivity. What is doing the explaining? Is time passing, right? This is doing the explaining, is the number of days. Those days will go from 1 to 20. This is what we've been given, right? So you will have days here, and here you have things like 1, 2, 3, 4, and then you're going to have a 10 here, and then 11, etc., up until to 20. And that's where something happens. There's a change that happens in there. Okay? Well, what is productivity? Hat, the fitted value of productivity, when post is equal to 0. Well, if post is equal to 0, it's simply just 4 plus 0.3 day squared. Agree? So when days is equal to 0, what's going to be my productivity? 4. What will happen to my productivity as days passes? It will increase, right? What would the data look like? Well, in day 1, you're going to have different level of productivities for different workers, different level of productivities for different workers, different level of productivities. But what you'll see is that this average thing is increasing. Okay. What happens at post? What happens at post? Well, at post, we see that we're going to have a decrease in productivity, in average productivity. By how much? By this 10, right? So at this stage here, imagine if this could continue on. If post didn't exist, this would continue like this. Agree? Because we have post, and post is saying minus 10 for all observation past day 10 or day 10 onwards, that means that that green line will be shifted down by 10 units. Would be shifted down by 10 units. So really this is what's happening to the continuation of this. You go down 10 units, and then you try to mimic that green line as much as you can, kind of like a parallel downward shift of that green line. Yeah, is everybody with me? Yeah. Okay, here's a challenging question. What if here you had plus 0.3 day times day squared times post? If you had something like this. Actually, let me make it 0.4. What would then happen to this graph? Well, if you had something like that, you're no longer just saying, oh, the post period, I'm going to have this lower productivity across all periods. But in the post period, it's also going to affect me. It's also going to affect productivity over time. It's also going to affect the slope or the rate at how quickly this changes. So in the post area, it's not going to change by 0.4. It's going to change by 0.4 plus 0.3 is going to change by 0.7, right? So it's true that this got lower, but if I had this extra bit here, then it could have been something like this. Okay, it could have been something like that. Everybody with me? Yeah? So hopefully you start to get this sense of like different dummy variables. When are they interacting? Where are they interacting? What's the difference? And the likes, okay? So you can get a sense of, you know, what's the appropriate econometric model to include on the different things. Yeah. Okay, we're getting close. 5.15. We have a regression. We're asking to do interpretations, which you should, you have them in the solutions, so it shouldn't be too much of a big deal. What is the expected level of patents when firm has not gone through a major merger? What does that mean? Merger is equal to 0. So don't be tempted here when you ask for expected level to find like a number. You don't need a number here, right? You need an equation. Really, all you need to do is go to this top equation here and just set merger is equal to 0. That's going to give you the expected value, okay, of those two things, right? Can you test the hypothesis? Sure, you can do a t-test on the two. Now, here's something that confuses people. Well, actually, let's discuss a little bit these two econometric models and what do they say in English. Okay, that's what I want to discuss onto this. In English, what does this model tell you about the effect of merger on patents? In English, that first model. Because merger only enters once as a dummy variable, that model is telling you that you believe that this merger is affecting patents, but it's affecting them the same regardless of the level of R&D, sales, or number of employees. So if you have merged, your patents will be higher across the board for all R&D, for all level of employment, so you're not discriminating between all of these different things. Okay? Yes? Everybody with me on that one? Yeah, so you're not really discriminating between them. What does the second model tell you? What is the view of the world that you have when you look at that second model? In that second model, you say not only will merger affect the level when research and development and L sales are equal to 0. So I will have a change in the amount of patents when these two are equal to 0. But merger will also affect the way sales and research and development affects number of patents. So I'm going to interact merger with the number of patents. Okay? So that's a slightly different story. Okay? That's a different story from the ones that we had before. Okay? And really, that's really the only thing that I want to add to this question, is for you to see a regression and say, what's the story in English? What's the difference? What are we implying in English about our hypothesis about the characteristics of this merger, or how this merger affects this, right? Note, for example, in here, we're assuming that the number of employees or the number of employees doesn't affect is not being affected. How the number of employees affects patents is the same across merged firms and non-merged firms, yeah? Part.
So, and would you say in the first model that merger is not unbiased because it's dependent on other variables in the model?
What do you mean is
Well, it's correlated. Isn't there like something when variables are correlated with other variables that violates?
Absolutely. If you believe so, I think your question is whether this is a bias or unbiased estimate, right? Or an estimator. That would depend on whether your A1 to A5 assumptions are violated, right? If you believe that any of this x's, not just merger, but any of this x's, is correlated with some error term or some variable in the error term, those will be, biased estimates, right? That would lead to bias. This model in itself, right, will not necessarily lead to bias or unbiased. This is not improving the bias or unbiased, because you still have the merger, research and development. You're not doing this because you expect it to be, it will come up with a less biased or less unbiased type estimator. Even though if you believe this is the view of the world, right? If you believe this is the view of the world, then all these interaction terms are in the error term, right?
Okay, so isn't it saying that like merger and log sales are correlated?
Not necessarily. Not necessarily. No. Not necessarily. Yeah. They don't have to necessarily be correlated there. Right? And if they were correlated, that in itself is not a problem, as long as they're not perfectly correlated. Okay, so that's all I have for that 515. The rest you can kind of look at a formula. 5.16, I think it's fairly clear. 5.17, assume female and white are completely uncorrelated with each other. Knowing that the share of females in the population is about 50%, and the share of white individuals is around 90%, do you think variance of beta hat female will be bigger than variance of beta white? Okay, well, this is a question of coming up with knowing the formulas for the variances, okay, and understanding what this regression, what these regressions are. Why will these two things be equal to 0 from the question? Because we are told that female and white are completely uncorrelated, right? So if I run a regression on female or white on female, I'm going to have an R square of 0. Sorry, I'm going to have an R square of 0. Yeah, they're perfectly uncorrelated with one another. So really, this boils down to which of these two is higher. Okay? Which of these two is higher? And we're told that female share of the population is about 50%, white is about 90%, so which one has the highest variance? Female, right? 50% of them are 0, 50% of them are 1. What about white? 90% of them are 1, 10% of them are 0. So the female one would have a higher variance, therefore the denominator will be higher, and hence this numerator will be lower. Okay. 5.8. We look at this model here. We have domestic and multinational corporations. One thing to notice here is that if you're going to look at this beta 1 hat will be the mean difference between multinational and domestic. When you test whether that beta 1 hat is statistically different from 0 or not, what are you doing? You're doing a t-test. What are you dividing by? by the standard errors. What are you assuming about those standard errors? That there is homoscedasticity. In this graph, you can clearly see that domestic have a much higher variance than multinationals, which means that homoscedasticity will not hold, which means that your standard errors will be incorrect, which means that your t-tests will also be incorrect, which means that it's not a valid test procedure anymore when you assume that you had homoscedasticity. So you have to assume heteroscedasticity for this to work. For question 5.19, I have created a video where some of your colleagues have taken different ways to answer this, and 5.20 really builds on that. So 5.20 proves to you what we have been kind of in lecture just assuming, that if you have a dummy variable type model, this beta here would exactly be the difference in means between the two different subgroups. Okay, so that's what you are trying to show here, right? And you can look through this. You can look through these manipulations, and if there's any bits on those manipulations that you don't quite understand, but if you were able to do 5.19 and you understand 5.19 enough, then it really builds on that, and it's a matter of just some manipulations on that particular bit over there.